Again, we will be continuing ahead with discussion of problems related to application of work energy theorem. And specifically, we will look at some cases of application of conservation of energy as well as work energy theorem in general. Okay. So we'll start with an example, which is actually directly from H.C. Verma. Now, this is a very important example to understand how we can apply the work energy theorem specifically in a situation like this. So we have a rough inclined plane at an angle of 37 degrees with respect to the with respect to the horizontal. And at the end of the inclined plane here, we have a spring attached. Okay. And a block is released from this position from initial speed 0. This has a coefficient of friction mu. Now given to us that the block is released from a position at 4.8 meters distance from the spring. Okay. And slides down to compress the spring by a maximum compression of 20 centimeters, and then slides up by a maximum displacement of 1 meter before stopping again. Okay, so from this information we have to find the coefficient of friction and we have to find the spring constant. Take G as 10 meters per second square. Okay. So this is directly one of the questions from the H.C. Verma exercise. So just think how you will set up the work energy equations. We will discuss in a moment. But just try to figure out yourself how you will set up the work energy equations. Pratyush, the maximum compression of the spring is 20 centimeters when the block pushes against it only, no? The spring obviously initially is uncompressed. As the block hits it, it's going to compress the spring to a certain maximum compression and then get recoiled back, no? So that maximum compression of 20 centimeters is because of the block hitting against the spring only. Understood the point, no? So initially the spring is obviously natural length. We'll have to assume it's a ideal spring. It's massless. Okay, so we'll compare three situations here. Okay. So this distance is 4.8 meters. So this is, let's say, position A of the block. Okay. Now what happens afterwards is that the block having started from A before, when the spring is at maximum compression, the block will be momentarily at rest. So let's take this as the position B of the block. So here, if this was a natural length, here this distance is becoming L minus 0.2 meters or 20 centimeters. Okay. So that means how much is the displacement of the block from A to B? This displacement is actually 5 meters. In 20 centimeters, no, that's 0.2 meters. So from A, that is the starting point, to B, when X is equal to maximum compression for spring and V is equal to 0 for the block. The block will momentarily stop when the spring has maximum compression. The displacement of the block is 4.8 meters plus 20 centimeters. That is 5 meters. Okay. And then from there, the block, so see what is happening in terms of acceleration. At this point of time, the block had an acceleration like this. But at this point of time, the block will have some acceleration, let's say E prime like this. So it will now slide back. But as it slides back, it's again going to have a maximum displacement of 1 meter up the inclined plane. So again, V is going to become 0. But at how much distance from the spring? Not 1 meter, but 0.8 meters. Because from this position, B was somewhere here. From here, it is going to be 1 meter. Understood now? So these are the three important stages of the motion. Yeah, of course, just before hitting the spring, it has some speed that is also there. But we don't want to calculate that speed. That is not important for us. Okay. So in between this and this, there is also that stage where it's about to hit the spring. So that point of time, the displacement of the block is 4.8 meters. Okay. And its speed is maximum. But this is not so important for us. What is more important for us is this picture and this picture here. So now you see if we apply, so first of all, we take a system as the block plus the spring plus the Earth's gravity. Okay. So spring force and mg, they are internal conservative forces. Okay. Normal reaction is there, but work done by normal reaction will be 0. And kinetic friction is there, and work done by kinetic friction will be the work done by non-conservative force. So there is no work done by external force on the system, but there is work done by non-conservative force. So we will say that in general, the application of work energy theorem, the statement of work energy theorem is that work done by friction will be change in kinetic energy plus change in spring's potential energy plus change in gravitational potential energy. This will be the application of work energy theorem for our particular system. Okay. So now we will apply this once from A to B and then from B to C, or we can even apply it directly from A to C. That's the interesting thing. So now apply this A to B and secondly B to C, or you can even apply it directly from A to C. Okay, and this will be an even better way of going about it. Okay, now when you apply it from A to B, you'll have to consider the vertical displacement of the block. So that will be this H1, which will become 3 meters because this angle is 37 degrees. Okay. And when you apply it from B to C, you'll also have to consider this H2, which will become 0.6 meters because this is again 37 degrees. And from B to C, this is 1 meter. Okay, so I'm putting up the equations in a moment. Just try to sort them out yourself. Change in total energy. Change in total mechanical energy. Yeah. It will be delta E, where delta E is change in kinetic plus change in springs potential plus change in gravitational potential. Okay. So anyway, let's apply this from A to B now. So A to B, you can see that work done by friction will be minus mu mg cos theta. Okay, all that you have now, because normal reaction that is going to be mg cos theta, because the components of mg are like this. So kinetic friction on the way down is mu n like this when the object is sliding like this. Okay, so A to B it's like this. So work done by friction is going to be minus mu mg cos theta into S, and the downward displacement from A to B. So that is going to be minus mu mg into 4 by 5, okay, into 5 meters. So minus 4 times mu mg. Okay, where this 4 is in meters, so this is in joules. change in kinetic energy will be 0 because u at A was 0 and v at B is again 0. It momentarily stops at the point B. Change in potential energy of the spring is plus half k x maximum square. That is half k into 0.2 square. So k is unknown here. Okay. And change in gravitational potential energy is minus mg h1. So that is minus mg into 3 meters. Just a second, the mass of the block, I think I've forgotten to write down the value. So anyway, we will set up this first equation and we'll see in the first equation there are two unknowns. Yeah, it's a 2 kg block. Okay, mass of the block is given in the question originally. Okay, just add that here. So this term, this work done by friction, can actually put its value in terms of mu now. So mg is going to be 20 newtons. So this is going to be minus 80 mu in joules because m is equal to 2 kg. This is 0, this is this much, and this is minus 60 joules. Okay, so we have minus 80 mu is equal to plus half k into 0.2 square minus 60. Okay, so we have 0.02 k, we solve this, is equal to 60 minus 80 mu. That's our equation 1 with the two unknown quantities. Okay, so just correlate this situation A to B with this. Now let's, Aditya, you got the answer for what? No, this is half, na? Half k into 0.04, so that's why it's 0.02. Okay, now let's apply the work energy equation from B to C. So for B to C, what is happening? The only difference is the block is moving in this sort of direction. Okay. From B to finally C, where it again comes to rest. Okay. So during that time, friction will be acting down the inclined plane. Rest of the things are same. And for some time, the spring force is pushing it like this and all that. But anyway, so work done by friction will be minus mu mg cos theta into the displacement from B to C. So this time it will be 1 meter displacement. So it will be equal to minus minus 16 mu in joules. Okay. Change in kinetic energy will again be 0 because velocity at B was 0, velocity at C is also 0. Change in spring's potential energy will be minus half K x maximum square. So that is minus half K into 0.2 square. And change in gravitational potential energy will be plus mg h2. So that is plus of 20 into 0.6. So plus 12 joules. Okay. So when we write this, work done by friction minus 16 mu is going to be change in kinetic energy, that's 0, plus change in potential energy of the spring, plus change in gravitational potential energy. So we have the relation minus 16 mu is equal to minus 0.02 K plus 12. Again, we have 0.02 K is equal to 12 plus 16 mu this time. This is our second equation. Now we can solve equation 1 and 2 for mu and K. So you can see, just equate them. So you have 60 minus 80 mu is equal to 12 plus 16 mu. So you have 96 mu is equal to 48. So mu is 0.5. So mu is coming out to be 0.5. And from that, you have K is equal to 12 plus 8 divided by 0.02. K is 1000 Newton per meter, or that's the same thing as 10 Newton per centimeter. So this is a very important example to understand the application of work energy theorem in any situation where you have a spring involved, where you have gravity involved, and you have kinetic friction involved. So please keep this example noted down as, a sort of standard way to understand application of work energy theorem for any system where we are dealing with these kind of things. Yeah, A to C is very interesting equation. We'll see that also, Pratish. We're coming to that. In A to C, remember, you have to consider the work done by friction as the whole path. It will not depend on displacement. It will depend on the whole path, A to B and B to C, because friction is what type of force? It is a non-conservative force. Okay, so next when we are going to consider A to C, we'll have to consider the fact that the point A was somewhere up here. Okay, and therefore this height is h1 minus h2. So that is 2.4 meters. We have to consider that. Change in potential energy ना बेटा, तो formula है ना, Durgesh, the change in potential energy of the spring is given by this formula ना, final potential energy minus initial potential energy. So when we are going from A to B, at A you can see what is the position of the spring, it's 0. At B you can see what is the position of the spring, it is compressed by 20 centimeters. So it's minus 20 centimeters. When you are going from B to C, at B, the initial position is the compression of 20 centimeters. At C, the final position of the spring is 0. So A to B, the spring is getting compressed, so its potential energy is increasing. Whereas when you're going from B to C, the spring is relaxing back to natural state. So it's losing potential energy. Okay, so hope it's clear this part. Okay, now before we proceed further, one more thing we'll understand here is, in a logical sense, energy wise, what is happening when we are going from A to B? What is happening in this situation? You can see that there is loss in potential energy, okay, loss in gravitational potential energy, that is resulting in a certain amount of gain in potential energy of the spring, because there's no gain in kinetic energy, net gain is 0. Okay, and that is also resulting in a certain amount of dissipation of energy by friction, by kinetic friction, because the work done by kinetic friction is negative. That means it dissipates energy from the system. There is loss of mechanical energy. So that is why the total loss in gravitational potential energy is greater than the gain in spring's potential energy. You can see that this side, the gain in spring's potential energy, this total thing is negative, no? Because this is negative. So the amount of potential energy that we have lost, the gravitational potential energy lost, is greater than the amount of gain in spring's potential energy. So the difference of the two, which is the total loss of energy, is the energy that is dissipated by friction. Typically it is dissipated as heat. Okay, so this thing. So the net loss in energy is the loss in gravitational potential energy minus the gain in spring's potential energy. So that net loss is equal to minus 80 mu, which is the dissipation of energy by friction. Whereas when you come to this situation here, going from B to C, you can see what is happening is that spring is losing potential energy. So loss in potential energy of the spring. So part of that is going into gain in gravitational potential energy. Okay. And part of that is again dissipated as heat. So it is dissipated by the kinetic friction. So the spring is losing this much energy, minus half kx square, this. Okay, part of it is going into this plus 12, which is a gain in gravitational potential energy, but part of it is dissipated as energy dissipated by friction. Okay, so that's how the second equation comes, and the rest of it was just solving of the equations. Yeah, whenever a particular force does negative work on the system, we say it dissipates energy. Because on the work done side, if you have a negative quantity, that means your total mechanical energy of the system on the right hand side is decreasing. See, we have this thing. This is equal to change in mechanical energy. So if this is a negative quantity, it is contributing to what? It is contributing to a loss in mechanical energy. So that means energy is getting dissipated. Dissipated का मतलब क्या है? Lost. Is it clear, Durgesh? Okay, just go through the equation solving part in the end also once more. Okay, now we'll also see that if we had applied the work energy theorem directly from A to C, matlab A to B and B to C, that path, then we could have avoided solving so much equation and calculated the coefficient of friction mu directly. But to calculate the spring constant, we will still have to involve one of these two other equations, either A to B or B to C. Okay, so now let's try to see what we'll get if we apply A to C. But remember, in this our path is A to B to C. So we have to consider that whole path. Starting from A, it is coming to the maximum compression position B, and then coming back to C. First it slid down all the way here. So this was much was this now? This was 5 meters. Then this displacement was 1 meter. And this height difference, therefore, is 2.4 meters. So in this, the work done by friction will be minus mu mg cos theta into path from AB, and then again minus mu mg cos theta from B to C. So it will be minus mu mg cos theta into 5 meters coming down plus 1 meter going up. So it will be minus mu into 20 into 4 by 5 into 6. So that's how much now? 16 into 6. So minus 96 mu. This is the net work done by friction for this path A to B to C. Okay. Change in potential energy of the spring will be 0 because at A, x of the spring was 0. And finally, when the block is at C, again the final position of the spring is 0. So this is the advantage. We bypass the value of K altogether. Okay. Change in kinetic energy is also again 0 because you can see at A, the initial speed of the block is 0. At C, again the final speed is momentarily 0. And change in gravitational potential energy is minus mgh. That is minus 2 into 10 into 2.4. So it is minus 48 joules. So we have work done by friction is change in spring's potential energy plus change in gravitational potential energy plus change in kinetic energy. So we directly have the equation minus 96 mu is equal to minus 48 joules. So mu comes out to be 0.5 directly from this. Okay. You will also notice that this is the same equation you will get, this one, this equation that we got. This is the same equation you will get if you were to add equation 1 plus 2 that we have done earlier. The two equations that we had got earlier, if you just add them linearly, I mean algebraically, you just add them, you'll get this equation. So this is a consistent equation actually. But as I said, this one will directly give you mu, but to calculate the value of k, you still have to use one of the other two equations, either A to B or B to C. Okay, so as I said that this is a very key problem to understand systems where we are dealing with springs, gravitational potential energy and friction together. Okay. Now we'll do one more example of an application of spring potential energy before we move on to other things. So in this next example, we have a situation like this. So we have an ideal spring like this. And the lower end of it is tied to a thread. And this thread now goes around a pulley. And the other end of the thread is again tied here. The spring is attached like this. Okay. Now this is a massless pulley, which itself is attached to a block. In a vertical situation. So this is a massless inextensible string or thread. This is a massless pulley. Now this block is attached to it. And this is an ideal spring. So it is massless. And given to us that the mass of the block is 5 kilograms. And the spring constant is, let us say, 25 Newton per centimeter. Okay. Now the block was initially held at rest such that the spring is relaxed, or it's a natural length state, and the thread is taut. So this thread is stretched out to its full length. It's not hanging loosely. Now at t equal to 0, the block is released. From this position. Okay. So first of all, if the spring stretches by x at some instant, then how much is the block's displacement? And secondly, find the speed of the block as a function of x, that is the extension of the spring. And from that, find maximum extension for the spring, and find maximum speed of the block. Okay, so this is a bit of an extension of the vertical spring mass system that we had done yesterday. Extension because now there is the complication of the pulley, okay, which is creating a sort of constraint relation. So we'll have to work out that constraint relation for part 1, and from that only you'll understand how to work out part 2, 3, and 4. So just try this out, people. Okay, so let's understand the first thing here. The displacement of the block will be equal to x by 2. So let's understand the reason for that. So one is you can just understand it as a matter of thread length conservation. Okay. So if this was the initial position where the block was being held at rest, so obviously some external agent was applying a force equal to the weight of the block. So the spring here is in the natural length position. And let us say this was some length L1. So this is length L2. So the thread length L is equal to L1 plus L2. And the natural length of the spring is L. Now after you release this at a certain instant, let us say the spring has stretched. It's become L plus X. And the block and thread together, the block and the pulley together have displaced by S downwards like this. The block has developed a speed V. So now you see this length here. This is how much? This is L1 plus S minus X. And on this side, this length is how much? It is L2 plus S. Okay. So this must be equal to L1 plus S minus X plus L2 plus S, because the thread length is constant. Okay. So you can see that L1 plus L2 must be equal to L1 plus L2 plus S, sorry, plus 2S minus X. So that is why S must be equal to X by 2. Okay. So you can simply understand that when you pull the block down through a distance S, now when the block displaces by a distance S, it's pulling the spring by how much? 2S. So obviously X is equal to 2S. Okay. You can also understand it by virtual power method. If you go by virtual power method, you can see that at some instant of time, if this end of the spring is the point P, okay, now tension in the thread is acting down at the point P, down at a stationary point here, upwards on the block. Now if the block at some instant has a velocity v downwards, okay, and the point P at that same instant has a velocity Vp downwards, okay, then the net power delivered by tension should be 0. So power delivered by tension at the point P is plus TVP, okay, and power delivered by tension on the block is minus 2TV, so that is 0. So this is equal to 2v. Okay. Now if this is L plus X, and this one is having a displacement in the downward direction as S, Vp is dx by dt. Is the rate at which the extension is increasing, and that is equal to 2 times ds by dt. Okay, so dx is equal to 2 times ds. So that means x is equal to 2 times s, or the displacement of the block is half the extension of the spring. So this is by the virtual power method. Okay. In this case, because it's a single pulley with a thread wrapped around, it's easier to just understand by thread length concept only. Okay. Now let us apply work energy also. From here to here, let us apply work energy theorem. Taking our system as the block plus pulley plus thread plus the spring plus gravity. Okay. So in that case, we can see work done by external is also 0, and there's no non-conservative force. So mechanical energy is conserved. Okay. Change in mechanical energy should be 0. So we have, going from here to here, initial speed was 0, now it's v. So change in kinetic energy, okay, change in spring's potential energy, here x was 0, here x is x, okay, so plus half kx square, plus change in gravitational potential energy, the block has come down by s, so minus mgs is equal to 0. Now we introduce the constraint relation. So this is our equation 2. Now introduce the constraint relation. So s is equal to x by 2 from equation 1. Substitute this here. So we have the relation half mv square plus half kx square minus mg x by 2 is equal to 0. So we have the relation that v square is equal to gx minus k by m x square, or v as a function of x is square root of gx minus k by m x square, where g is 10, okay, k is 2500 Newton per Newton per meter, substituting this in SI unit, and mass of the block was 5 kg or whatever. I don't remember the values were taken. Yeah, 25 Newton per centimeter. So that's much, and 5 kg. Okay. So v as a function of x is square root of 10x minus 500 x square. Now next, from this relation only, we will find out the maximum speed of the block as well as the maximum extension of the spring. So the maximum extension of the spring you will see is the value of x when v is 0, and that will come out to be 2 centimeters. Okay, so I'm just minimizing this a little bit for you to go through. Yes, x will be maximum when v is 0. That's correct, Pratyush. So from this equation, you can see that x will be equal to x maximum when v is 0. So that means 10x minus 500x square should be 0. That means either x is 0, which was the initial state, or x is equal to 10 by 500 or 2 centimeters. So this is the maximum extension. Okay. Now, the other thing is you can also understand logically that since it's an oscillation, okay, here also the block oscillates vertically. Okay. Between x equal to 0 to x equal to 2 centimeters. That means displacement 0 to displacement equal to 1 centimeter. The v equal to v max is at the mean position. So mean position will be at x equal to 1 centimeter, or that is the same thing as a displacement of half a centimeter. So you can understand this logically, or we can use maxima minima also. Okay. So v max will be equal to square root of 10 into 1 centimeter, which will convert into meters, of course, minus 500 into 1 centimeter square. So it will be square root of this. So this will become 5 into 10 raised by minus 2. So square root of 0.05 or square root of 5 by 10 meters per second, or 10 root 5 centimeters per second. This will be the maximum speed. Okay, I'll tell you the maximum minimum method also, but first you can just understand it this way. Okay. So from the above expression of v, and then logically we are understanding that the block oscillates vertically between x equal to 0 and x equal to 2 centimeters. So at the midpoint, you will have the mean position. Mean position will be the midpoint of x equal to 0 and x equal to 2 centimeters. So mean position is where in an oscillation we have the maximum speed. Okay, now we can also understand this by maxima minima concept. So alternately, we can understand that V was square root of 10x minus 500x square. So it's like V is square root of some kind of function of x, where that function of x is 10x minus 500x square. So for V max, first find the maxima of fx, and then V max will be equal to square root of that maxima. Okay. So to find the maximum of the function, you know what to do. Okay. This is a quadratic function. So you know its graph is like this. You don't even need to use this thing. You don't need to use differentiation. You can see the roots are 0 and 50. Sorry, 0 and 1 by 50. So this will be maximum at 1 by 100. The vertex of the parabola is at midpoint of the roots. Okay, so y's maxima you can see is the value of the function at x equal to 1 by 100, which is the same thing we've understood here, x equal to 1 centimeter. So that is nothing but so this is y's maxima. So therefore v maximum is square root of that function's maximum. So v maximum is square root of 5 by 100 in meters per second. So that's the same thing what we got here. So this is the maxima minima method. If you're confused about the graph and all this, you can also use this, that dy by dx should be 0. So differentiation of 10x minus this should be 0. And second derivative should be negative. So you can go with that method also. Whatever is preferable to you as a method for finding the maxima, you can go with that. Okay, so hope the application is completely clear here. Okay, now let's move on to a different type of question now. So with these examples, you should be able to handle any type of system which has spring mass kind of application and application of potential energy of the spring. Now we'll move on to a different type of question involving work done by friction. Okay, and a very interesting question at that. So we'll see a situation where the amount of frictional force acting is variable. Okay, so you have a rough surface with coefficient of friction mu, and on that we have a chain like this. A chain, or a, you can say, heavy rope. So this is a heavy rope of mass capital M and total length L. Now when it is released from this position, it just about starts slipping. Okay, so if the heavy rope is released with 1/3 of its length, hanging vertically, then it just starts to slip. Okay, so first of all, find the coefficient of friction, and second, find the speed of the rope at the instant when it is just about to slip off from the table completely. Okay, so just note down the question first. We'll discuss more about this. Okay, so let's understand the first part. If it's just about starting to slip when this length is L by 3, okay, it means that the friction acting at the top is limiting friction, okay, but it's just about to accelerate. So let's understand what's happening when it just about starts slipping. So the condition for it to just start slipping is that this horizontal acceleration here and this vertical acceleration A is just about tending to 0. Okay, when on this vertical section the tension is like this, on this horizontal section the tension is like this. Okay, there is 2/3 of the weight acting here, creating normal reaction and kinetic friction mu n, and 1/3 of the weight here, because this this length here, this top portion's length will be 2/3 of the total length. That's why. Okay, so if we consider this end of the chain A, this end of the chain B, and the corner point P, so think of the section AP of the chain or of the rope. So if you think of the section AP and only its free body diagram, so you'll see that this is being pulled with the tension at the corner over here and pulled back by kinetic friction here because its acceleration is tending to 0. The weight of this section is 2 by 3 mg because the mass is 2 by 3 m. So the normal reaction is balancing that. Okay. So for this section, the equation becomes T is equal to kinetic friction, which is mu n, and n is equal to 2 by 3 mg. Okay. So this is that T is equal to mu into 2 by 3 mg. This is one equation we have. Okay. Now we also have the vertical section of the chain or the rope. So for the vertical section, what is happening is this the same amount of tension. Now why we've taken the tension same over here? Because the part of the chain which is going around the corner, that is of negligible mass. Okay. So it's like this. If you magnify this part at the corner, it's like this. So we have mentally divided it into this portion and this portion. So here, if this tension is T1 and this tension is T2, T1 is equal to T2 more or less, because the mass of the section in the corner, that is negligible. This section which is going around the corner, okay, from this to this, its mass is negligible. We write this as a delta m, it is tending to 0. So that's why we can take the tension in the vertical section at the top to be more or less equal to the tension in the horizontal section at the end P. Okay. And this one's weight is m by 3g, and again its acceleration is tending to 0. So for this one we have the equation now that T is equal to m by 3g. Okay. So now comparing this and this, we can see that 2 by 3 mu mg is equal to mg by 3. That means the coefficient of friction is 0.5. That is the first part. So this is the solution of the first part. Just go through it carefully. This is nothing to do with work energy. This is an application of the concept of friction and free body diagram, limiting friction and free body diagram. It just about starts to slip with L by 3 hanging. That means if I keep more than L by 3 hanging, it will slip with acceleration. If I keep less than L by 3, it will not slip. So when I keep L by 3, the tension is just about enough to balance the kinetic, the limiting friction, and it starts to slip with an acceleration tending to 0. Okay, so now let's come to the second part. We want to find the speed at the instant when the chain has just about slipped off. Okay, so for that we will consider a comparison of the chain at 3 different points of time. One when it's starting off its motion, second at some time in between, and third when it's just about to slip off completely. So we'll compare these 3 situations. So to compare these situations, this was the state initially when the motion began. 1/3 is hanging, 2/3 is on the surface. This is at some point of time in between, let's say. Okay. And this is when we want to find out, just slipped off the table completely. So it's like this. Okay. So here, this is 2L by 3. This is L by 3. Okay. The speed of the chain is 0 at this point of time. Okay. And it's just about starting off with an acceleration tending to 0. Now, by now, what has happened is, suppose this end of the chain has displaced by distance x. So this end of the chain is also displaced by x. So this length now has become 2L by 3 minus x. Okay. And this length has become L by 3 plus X, this total length from here to here. Okay. So by now the chain has developed speed V and also has acceleration. And now of course the entire chain is here. So by now the speed is some V naught, which we want to calculate. So we will say that if we take my system as the chain or rope, whatever, plus gravity, okay, then work done by friction is equal to change in kinetic energy plus change in gravitational potential energy. So now the thing is, to calculate work done by friction, we will need to use integration. We'll have to use integration because kinetic friction will be a variable force. Why? Because normal reaction is variable. It's a function of x. So let's look into that thing first. Okay, so in this second diagram, if you look it into the free body diagram of this portion AP, we can see that the weight of this portion is this much. Okay, mass of that portion AP is mass per unit length multiplied by length of the portion AP. So that is a concept we are using for weight. So that is equal to normal reaction, and the kinetic friction is mu n. Okay. So now if this portion goes through a small displacement of dx in this direction, the work done by friction for that small displacement will be minus of this into this. So that will be minus mu n into dx. So that will be minus mu into the weight. Okay, normal reaction will be equal to weight. So you can write this like this. This will be the work done by friction for that small displacement of dx. Okay. So now going from initial situation where x was 0 to final situation where x is equal to 2l by 3. So in my above diagram, that was figure 1 and this one was figure 3. Okay. This one is the in between figure 2. Okay. So the total work done from this to this is going to be integration of this from 1 to 3. So that is going to be integration of minus mu g by L into 2 by 3L minus x dx, going from x equal to 0 to x equal to 2L by 3. So work done by friction is minus mu mg by L. Now this integration will give us 2L by 3x minus x square by 2 from x equal to 0 to x equal to 2L by 3. Okay. So the upper limit will become 4L square by 9 minus 2L square by 9. The lower limit is 0. So 4 minus 2, that's 2. So minus mu mg by L into 2L square by 9. So the work done by friction expectedly is negative, but it's equal to how much? Minus 2 by 9 mu mg L. And remember, we already know that the value of mu is 0.5. That was what we had calculated earlier. Okay, so this is the work done by friction. And of course, next we will consider the change in potential energy so that we can then apply work energy theorem and calculate the overall change in kinetic energy. Okay. First, make sure these three diagrams on top are clear to you. Figure 1, 2, and 3. 1 is the initial state, 3 is the final state when we want to find the speed v0. But 2 is some intermediate state, when the chain is in the process of slipping off from the initial part 2L by 3 on the table to the final part where 0 part is on the table and the entire chain is hanging vertically. So when it just about slips off the table, this is the situation with what we've got in figure 3. But as it is going from 1 to 3, the amount of frictional force acting is variable. So the work done by friction has to be calculated by an integration. Okay, so now we have work done by friction. Okay, and we want to find the change in kinetic energy so that we can find V0. So we need to basically calculate the change in gravitational potential energy. So let's see how we'll do that. So for change in gravitational potential energy, we have to consider like this. For delta U gravitational, once again, you compare the initial state with the final state. So now let's say that I'm using the ground level as my reference level. So here in the initial situation, I have 2m by 3 and some kind of height h, and m by 3 whose center of mass here is at a height of how much? This center of mass will be at L by 6. So this is h minus L by 6. Okay. And here I have the entire mass such that the system center of mass here is at L by 2 from the top. So the height of the center of mass is h minus L by 2 from the reference level. Okay. Yes, no, that much you have done in center of mass till now, no? So you know that uniform distribution of mass, the center of mass is at the midpoint. Okay, but it's a uniform change, so we'll take the center of mass as this. Okay, so this one center of mass is here, this one center of mass is here. Okay, so the change in potential energy will be like this. Here, if you consider the initial potential energy, we can take this as 2m by 3 g h plus m by 3 g h minus L by 6 with respect to this reference level. With respect to the same reference level, we can write the final potential energy as mg into h minus L by 2. Okay, so you will see that when you calculate this, this becomes mgh, because this and this adds, minus mg L by 18, and this becomes mgh minus mg L by 2. So this is my initial potential energy with respect to this reference level. This is my final potential energy with respect to the same reference level. So my change in gravitational potential energy will be independent of the reference level. So it will be independent of h. It will be final minus initial. So mgh term will cancel out, because as far as the change is concerned, the reference doesn't matter. Where we take the reference will not play a role. So it is mg minus L by 2 plus L by 18. Or you can write this as minus mg L by 2, 1 minus 1 by 9. So minus 4 by 9 mgl. That is the change in gravitational potential energy. And it's expectedly negative because mass is coming down. So this is our change in gravitational potential energy. Now we have to just put together the work energy situation. Here U was 0. By now the speed has become V0. So change in the work done by friction is equal to change in kinetic energy plus change in gravitational potential energy. So the work done by friction from above was this much, minus 2 by 9 mu mgl, and mu itself was 0.5. This is equal to half m v0 square, where v0 is the speed when it just leaves the table, minus 4 by 9 mgl, and the value of mu here is 0.5. So we have half m v0 square is 4 by 9 mgl minus 1 by 9 mgl. Why 1 by 9? Because mu is 0.5. So 3 by 9 or 1 by 3 mgl. So V0 you can see is becoming square root of 2 by 3 gl. So this is the speed of the chain or the rope as it just slips off. Okay, people. So again, this is an advanced level question, more tricky than the standard applications of work energy, because there is variable force and you have to do the work done by friction by integration. So make sure you revise this, but the level of questions for the coming test on 20th will not be this. It will be easier. It will be the type of level of questions we have discussed till yesterday, and conceptually it will be till lecture number 4. That is the concept of potential energy, conservative, non-conservative force, and definition of work energy theorem. Okay. So that's it for today's session, people. Now you can complete most of the questions in HC Verma. Now you'll also find that there are some questions in related to power delivered by a force. So you can leave them out for the moment, even though from your previous chapter, you know the definition of power. It is the rate of work done with respect to time, but we'll be discussing power in the next lecture. Okay, so don't worry about those questions yet. Okay. Yeah, I will send the recording for both yesterday and today's lecture along with the notes. So yeah, there'll be a couple of more lectures because few more things have to be discussed. But HC Verma level work energy is done, so you can work out the questions, and we can also discuss doubts in the next lecture. So that's it for today's session, people. People wishing you all the best.